Any more questions? If not, then this concludes the second session of the morning. Please, then the speakers for an excellent presentation. Thank you very much.
We presented here covering a bit of a diversity of topics. The first relates to the development of reactors at Sasol, more generally than perhaps the previous presentation this morning. It is to be delivered by Dr. Anton Vosloo. Anton has been with Sasol now some 15 years. He currently holds the position of the Director for the Catalyst Research within Sastec R&D in Sasolburg. And I think comes to Sasol from an academic career previously at the University of Stellenbosch, but I guess in many ways has made his major contributions through working with Sasol. Anton, welcome, and we look forward to your presentation.
Mr. Chairman, ladies and gentlemen, thank you for the introduction. I'm going to talk about reactor development at Sasol. And I also want to recognize the contribution of my co-author, Mr. Andre Steinbach, that was very much involved in the development of both the slurry phase reactor as well as the high temperature stone-cooled reactor. What I'm not going to do today is to give you a fundamental discussion on how to design and build either high temperature or low temperature Fischer-Tropsch reactors. That we can pick up in any textbook. What I'm also not going to do to tell you today is which of those models are applicable and how we have modified some of those models, because that is proprietary information. But what I will do is share with you some of our design methodologies, our approach, why we feel comfortable when we scale up from the one side to the other one. As an overview of my presentation, I will just give you a brief introduction to Sasol, and that will be quite brief. Then I will discuss the high temperature Fischer-Tropsch reactors, firstly the circulating fluidized bed reactor, followed by the Sasol advanced Sasol. Then a very brief look at the low temperature Fischer-Tropsch reactors, the tubular fixed bed or the ARGI reactors, then the slurry phase reactors as developed for iron and also for cobalt, and I will end with the normal conclusions. First, the introduction. The company was established in 1950. We are 50 years old. There's actually a mistake on the slide. There should have been an emblem there of 50 years, but I couldn't get that one. I don't know how to put it onto my slide, so unfortunately you have to bear with me. The official birth date of Sasol is the 26th of September 1950. Although the company was established in 1950, it came in production in 1955, in August 1955. In fact, that was the first products from the gasifiers. As Mark Bryce said this morning, the reason for the existence of Sasol was to build synfuels plants to produce liquid fuels from coal. We have gambled on the oil price at that stage. We have lost the gamble on the oil price. We have also gambled on the technology. Both the low temperature process as well as the high temperature process at that stage were not fully commercialized. It is true that during the Second World War the Germans commercialized tubular fixed bed for fuels production, but that was based on cobalt. It was not based on iron. So we were in both respects the guinea pig of the world with regards to low temperature and high temperature Fischer-Tropsch reactors. Now at Sasolburg, as I said, we had the tubular fixed bed reactors as well as the circulating fluidized bed reactor. And later this plant was converted to low temperature FT only. Obviously that was after Secunda came in operation and the plant becomes uneconomical if you only produce synfuels at that small scale. And currently we are operating tubular reactors and a slurry phase reactor at Sasolburg. The second production facility came online at Secunda in 1980. Think back what Mark said this morning about the oil price. We just caught the wave on the upward side for the oil price in 1980. And that plant was only high temperature FT. So Mark's proposal to build an FT, low temperature FT plant was not successful, as he said this morning. The current capacity of Secunda is about 150,000 barrels per day of fuels equivalent. We do not produce 150,000 barrels per day because we also produce chemicals. That's one of the reasons why Secunda is quite profitable at this stage. And the CFP reactors has been replaced by SAS reactors, but we do still operate some of those CFP reactors at the moment. But let us have a look at the high temperature FT. The circulating fluidized bed reactors were commissioned in 1955, 2 of them. As Mark said this morning, it was based on the Kellogg design, and the reactor consists out of a reactor section and also a catalyst hop, and I will show you a diagram which I've already seen today as well. Very important, it was a significant scale-up, from a couple of barrels per day to about 2,200 barrels per day. Unfortunately, that scale-up was not immediately successful. For those of you that are involved in to be the licensing business, this is your worst nightmare that can come true when your reactor, after initial stage, does not meet the licensing requirements. The situation was so bad at that stage that the intellectual property rights were transferred to Sasol. So willingly or unwillingly, we became the proud owner of fluidized bed technology as applied to Fisher-Tropsch reactor. That had a significant impact on how Sasol, especially in the early stages, viewed technology development, and I will come to that point later. Luckily for us, we managed to get that reactors online, we get them to operate, and I will discuss some of the problems as well. And it operated, and we were so successful with the fluidized bed reactors that when this decision was taken to build Secunda, that it was based on the Sasol reactors, and it was scaled up to about 6,500 barrels per day, and the first plant came online in 1980, and as Mark said, very soon afterwards, we had Sasol 3, which was more or less a duplicate of the Secunda facilities. And then in 1980, and then in 1992, 3 circulating fluidized bed reactors were commissioned at Moscow. And I will come back later to those reactors as well. Okay. This is a schematic diagram of the reactor. You've seen that. Cooling coils inside the reactor, a hopper section, a standpipe section, cyclone in there. One thing that wasn't mentioned this morning, but what is very important, it was mentioned, but I want to put more emphasis on it, and that is the pressure balance across this reactor. It is important that this whole configuration must be such that the pressure drop across your reaction section must be recovered due to the density difference between the standpipe and the reactor. So that standpipe must be long enough so that at that point there, that's the highest pressure point, it's over there, and the lowest pressure point is over there, so that you recover your pressure drop. Otherwise, you will have backflow, you will have gas going through this side instead of through the reactor. That's also one of the reasons why the reactor was not successful when we started up in 1955. Design and operating problems. Those are not in sequence, it's just a list of some of the major problems which we had with the circulating fluidized bed reactor. Remember, I said it was an extensive scale-up, a couple of barrels a day to 2,500 barrels a day. In the 1950s, they did not have computers. Finite element method was in the development phase, so they could not really analyze from a structural point of view how this big monster is going to operate in terms of vibration. So there were excessive vibrations on those reactors at the beginning. So we had to dampen them as well. Another problem which we had was erosion, both in the riser section and also in the gooseneck section. So we had to find the right refractory material to prevent that erosion. Big problem was catalyst hang-up in the hopper or rat holes, so that we could not recover the pressure drop particularly. So that was solved by changing the angle of the hopper, and you've seen some of the diagrams where the angle was changed from 60 degrees to 80 degrees to overcome that problem. I've already spoken about the pressure balance. Very important is if you look at the original design, there was a fixed tube cooler inside, actually 2 of them. And the catalyst in the gas was in the tube side, and the cooling was obviously in the other side, and it was oil cooled, it was not steam cooled. And those fixed tube seat cooler gave us a lot of problems. First of all, some blockage problems, as David also said. There were some erosion problems, corrosion problems for those coolers. There was at the bottom end of those coolers, stalactites were being formed. So later, we have changed those coolers and it has been replaced by cooling coils, and those cooling coils are working extremely well in both the circulating, well not both, but the circulating fluidized bed reactors, the advanced simple reactors, and also in the study bed reactors, which I will come to. Another very important part of the circulating fluidized bed and also the SAS reactor is the cyclones. And we had 2-stage cyclones, and those were replaced later by single-stage cyclones. And so we can go on, and there were a lot of problems. But since 1955, up to the point where we have decided to build Secunda, we have ironed out all these problems, and the reactors were working satisfactorily. Not 100%, there were some minor problems, but we could live with those problems to the extent that we were willing to build this big plant in Secunda. There's actually one big problem with this type of reactor. It's expensive to build and expensive to operate as well. So we decided to have a relook at the circulating fluid, at the normal fluidized bed reactors, in spite of the successes at Secunda and later on at Vosloo. As Mark said this morning, in the early 1950s there was a fluidized bed reactor in operation in Brownsville, but apparently it was not successful. And as Mark also said this morning, what is quite ironic, is that we have operated fluidized bed pilot plants, not for the reactor development, but for catalyst development. So if we were successful in operating those fluidized bed pilot plants for catalyst development, why should we not be able to be successful in build bigger fluidized reactors as well? And that was one of the main reasons why I've decided to have a relook at this fluidized bed reactor concept, or the normal fluidized bed reactor. So, in spite of the successes which we had with the circulating fluidized bed reactor, we want to move further on. Those pilot plants actually can take about a couple of kilograms of catalyst. It's not really suited for reactor development. It was not designed for that. So we had to go to larger scale reactors. But we didn't immediately build a big pilot plant. We first did extensive cold model studies on a 14 centimeter internal diameter cold model to look at the fluidization properties, and it has been published and documented quite extensively, so I will not go into those results. But this led to the construction, the design and construction and commissioning of this 100 barrels per day demonstration reactor around about 1983 and 1982. So we know how to produce a catalyst. We have looked at the fluidization properties and cold models. Now was the time to do this fluidization on a larger scale. Cold models for FT is not really sufficient because you form carbon with iron at those temperatures. So your catalyst density is changing continuously. Your particle size is also changing as well, but not to the same extent as your density. So you have to do these studies at realistic operating conditions. So you need a reactor like that, otherwise you will not be able to design a commercial sized fluidized bed reactor. We were quite successful with that reactor. We could get stable fluidization. We looked at all the internals of the reactor, we looked at the gas distributor, we looked at the cooling coils, we looked at the cyclones, and we've determined what the catalyst density must be and what the particle size distribution must be, and we looked at the linear velocity through that reactor. So we did all the things that is needed to design a full-scale commercial reactor, and we were successful. And okay, so there is a diagram of the reactor. You've seen it this morning. It is much simpler than a circulating fluidized bed. The gas distributor, the cooling coils, the cyclones. The one thing which you have to remember when you operate this reactor, because you have a continuous change in density, if you're not careful, you can have a bed expansion that goes beyond that point, then you can blow out all your catalyst from your reactor. Such a problem you don't have with the circulating fluidized bed reactor, but you do have it with a SAS reactor. Some of the advantages, there are two big advantages of this reactor, except now for cost. And that is if you look at the catalyst consumption, it's about 50% of a simple reactor. And why is that so? The reason is that in a circulating fluidized bed reactor, only 50% of your catalyst is in contact with the gas. The other 50% lies in the hopper. So they're doing nothing except building up pressure in the hopper. It's also more thermal efficient due to the high steam pressure. You may ask the question, why? An FT reactor is in essence just a heat exchanger. If you look at the SAS reactor or the slurry phase reactor, it resembles a heat exchanger. So in many cases you are limited by the amount of heating capacity, heat removal capacity which you can put into that reactor. For a circulating fluidized bed reactor, the diameter of the reactor must be much smaller so that you can have higher linear velocities to have a circulating fluidized bed reactor. And that means that you can pack less heat transfer area into that reactor. For the SAS reactor, you can make the reactor much bigger, so you can put 50% more heat transfer area into that reactor. That means we can raise the steam pressure. Yeah. And because when we operate at the higher steam pressure, our thermal efficiency becomes better. Obviously, mechanically, it's far less complex. It's a very smooth reactor. You don't have this lot of vibration in it. You have increased single train capacity. The CFBs are limited by about 8,000 barrels per day, and that limitation is due to the size of the hopper, which you have here. The SAS this morning we said 22,000 barrels per day. It can higher. It will depend on the mechanical considerations, and also on the recycle compressor will also determine what the maximum size will be here. But there's nothing from a process point of view that prevents us to build much larger reactors than we have at the moment. The operation is much easier, except now for the point which you have to remember, to have a very careful look at the bed density. Otherwise you can blow out all your catalysts. This is not an advantage, but you must remember you must have more than enough catalysts to cover the cooling coils. As I've said, it's basically heat exchangers. You have much more catalyst in that reactor. That is what's really needed, because we have to cover the cooling coils. And the stability of this reactor is determined by the cyclone operation. It is almost as easy as that at this stage. To operate an advanced simple reactor, you operate cyclones. And the other advantage, the much lower capital costs, and you've seen some of the figures. Here's a bit of the history. After 1983, we were successful with our demonstration reactor. We designed and built the first 5-meter internal diameter reactor and was commissioned in 1989, and roughly about 3,000 to 3,500 barrels per day capacity. And we operated that reactor for a couple of years quite successfully at Sasol. Then we've used that design to build the second generation SAS reactor in 1995, and that reactor had an 8-meter diameter or 11,000 barrels per day capacity. And here we did get some surprises when we moved from the 5-meter to the 8-meter. Not major surprises, but there were some differences, especially in terms of selectivities. What is quite interesting is that the methane selectivity from a SAS reactor is significantly less than that of a fluidized bed, a circulating fluidized bed reactor. So that's also another advantage of the SAS reactor. Because of the success of that reactor, the decision was taken, and it was a very bold decision, I must also say, to replace at one stage all the circulating fluidized bed reactors, and also at that stage we decided to replace the ignition catalyst and the reformers also with the hydrotopso open flame reforming technology. So what Sasol's top management has decided at that stage is to have in effect a total heart transplant at our Secunda facility. We replaced all our circulating fluidized bed reactors with the SAS reactor, and simultaneously we replaced the burners on top of the autothermal reformers as well. A very brave decision, I must say. So now we have 22,000 barrels per day reactors in operation. All the CFB's reactors will be decommissioned sometime or the other, but you know how it is. You build the synthesis capacity, you increase your syngas production capacity, and then nobody wants to shut down the CFB. Because, especially now with the oil price so high, the more we produce, the more money we make, obviously. But the CFBs are still in operation at Moscas. Actually, those CFBs are performing extremely well at Moscas. Moscas has looked at the operating procedure of those reactors. They have further refined it to the extent now that the reactors that you will see at Moscas, the 3 of them, well, if you go down there, has an online availability of more than 99%. That's an extremely high online availability. So one can successfully operate circulating fluidized bed reactors for Fischer-Tropsch applications. And let us turn to low temperature F2 reactor. As I said, the tubular fixed bed reactors were commissioned in 1955. 4 Argy reactors, but the capacity is about 500 barrels per day. Very small reactor figure. But unlike the circulating fluidized bed, our gamble came off with this one. There were no problems really during commissioning. So it operated quite smoothly. And the reactors remained almost unchanged up to date. We have replaced the tubes in two of these reactors, so 2 of them are still the original reactors. They still have the original recycle blower working there as well. What we have done is to optimize the operating conditions and also to optimize the catalyst composition. The catalyst is now much more active. We have a very high wax selectivity from those reactors. We have increased the throughput through the reactors that we do. And then in 1989 we have commissioned a high pressure reactor, about 40 to 50 bar reactor. Because if you can remember back to the kinetic equation which Mark puts on the board this morning, if you increase the pressure for iron catalyst, you will increase the activity or the reaction rate. Not so for cobalt, but definitely so for iron. So we have commissioned that reactor, and it has a capacity of 700 barrels per day. Not a dramatic increase from 5 to 7, but some increase again. The disadvantages has been published extensively, expensive. Heat removal is quite a problem for very active catalysts because you have radio and axial profiles in the. This is also once again the diagram of this reactor. One thing which I want to mention about this reactor, which is not mentioned, is to unload that reactor. There's actually a guy standing at the bottom of that reactor. Standing there. You swing this back, and then you open that slide valve over there. And this guy is standing at the bottom with the catalyst raining down on top of his head. It's not a very nice experience for that guy to do. But what we've managed to do is where originally when this reactor was commissioned, the turnaround time between catalyst changes was more than a week. It's now about 1 day. Since you cut gas, so gas in is less than 1 day. It significantly improved the online availability of this reactor. There's nothing wrong with those reactors except that they are expensive to build. So I don't think we will ever go down this route again. Now let's have a look at the low temperature slurry phase reactor. The development work started in the 1980s, in spite of the fact that Sasol's top management turned down Mark's approach to build low temperature FT reactors at Secunda. We do not claim that we have invented the slurry phase for Fischer-Tropsch, because if you go through the patent literature, you will see that there's an American patent in 1942 that made reference to slurry phase for Fischer-Tropsch application. Professor Kobel did extensive work in the 1950s. But there's one big problem with the slurry phase, especially with iron, and it's how do you separate the catalyst from the wax? So what we decided to do in the 1980s is to have a real look at the work which Kobel had done and see if we can reproduce those results with iron, and also solve the problem with the catalyst wax separation, because we were successful with the SAS reactor. And so the engineers had to do something in process development, otherwise we were out of jobs. So we converted one of our tubular pilot plants is a 2-inch tube, about 12 meters high. We converted that to a slurry phase reactor. To see at least if we operate in slurry mode, can we reproduce the results from Kobel for iron with our catalyst? And also to start looking at how we're going to solve this problem to separate the catalyst from the wax. And we were really quite successful. Remember in 1983 we have commissioned that 100 barrels per day demonstration reactor, and in 1989 we built the SAS reactor. So we have now completed our development work on the SAS reactor, and this 100 barrels per day reactor became available, and we've decided to convert that reactor to a slurry phase reactor, and it was recommissioned in 1990 as a slurry phase reactor. So it started off life as a SAS, and then it was reborn as an iron-based slurry phase reactor. Major breakthroughs for this was the development of the catalyst wax separation, and in parallel with that, the development of a new iron catalyst. We had to have a real look at our iron catalyst, and we came up with a new catalyst as well. This reactor was successfully commissioned. In 1993, the first commercial reactor was commissioned. Now, if you look at that time span, 1990 to 1993, I've made the comment that Sasol was severely hurt in the early 1950s. Due to the fact that that technology did not work, the fluidized bed technology. That made us, from a technology point of view, a very conservative company, because we went through that experience. But because of the successes of the SAS reactor, when we scale up to the 5-meter reactor, also the successes on the circulating fluidized bed reactor, Sasol's top management decided at that stage, when the detailed design was almost completed for 2 large tubular fixed bed reactors to be built at Sasolburg, this is not the way to go. We have reached a point in the development of the slurry phase reactor that we could go to the board and say there is still risks, but the risk can be managed. We suggest that you should give serious consideration to change the whole nature of this project and move from fixed bed to slurry bed. As Ben Jager has always said in the past, nobody liked R&D at that stage. Not the production people, because they are accustomed to operate tubular fixed bed reactors for 30 years, and they operate very nicely. The design people didn't like this because they have to change the design. And even the project people, they don't want to change horses during detailed design phase. But in spite of all those arguments against the technology, it was not fully developed, it was in the development stage, there were some major problems still. The decision was taken that yes, you will go the slurry bed route, you will not go the fixed bed route. And luckily for us, it was successful. And that reactor was commissioned in 1993 with online availability of 98% during the first year. It was never shut down in that first year due to a process reason. I think that is quite an achievement for the first of its kind technology. You see, it looks like a SAS reactor because in essence it is a SAS reactor. It's just at low temperature. Now that was fine. We have not abandoned iron, but we've also moved on to cobalt catalysts as well. And we had to have a relook at the design of a cobalt-based study phase reactor because you cannot just take an iron reactor and just replace the catalyst with cobalt in it. So we have done extensive work on the redesign of the reactor internals, especially our catalyst wax separation system. At this moment, it's about 10-fold more efficient, and the throughput through that system is also 10-fold better than for iron. So we have a very, very efficient system to separate the cobalt from the wax at the moment. We have used our 100 barrels per day demonstration reactor extensively to obtain design information and also catalyst lifetime verification at that scale. So we are now ready, as FT licensor, we will guarantee at least a single reactor train of 17,000 barrels per day. And why are we confident that we can go from 100 barrels per day to 17,000 barrels per day? Is if we look back at our track record. If we obtain the design information on that demonstration reactor scale, combine it with our fundamental understanding of the hydrodynamics, the kinetics and the selectivities, we were successful in the past. We have verified our models, and we are also confident that from a process point of view, we can scale up to 17 or 20, whatever the case may be.